As it happens, almost everything in the night sky emits energy in the form of these same micro and radio waves. Here is the Milky Way photographed in visible light. And here is its image at radio wavelengths. After World War II, this new way of looking at the sky launched the field of radio astronomy. And now, it would lead to a phenomenal discovery. Robert Wilson and Arno Penzias were both experts in the new fields of radio and microwave astronomy. And in 1964, AT&T's Bell Labs asked them to help figure out what might be causing the annoying hiss in satellite communications. To do so, they began their detective work with this giant antenna that could receive signals from Telstar. To test the instrument, they pointed it at an empty patch of sky. Aiming at nothing, they expected to find nothing. Instead, to their surprise, they picked up a faint microwave signal, apparently coming from empty space. Our entire universe had actually been born in a tremendous burst of energy billions of years ago. Team leader Bob Dickey believed that some of that energy should still be detectable as a faint hiss of microwaves in space. In the Big Bang, our entire universe, all the matter, all the energy that would ever exist, burst into being at a single instant. A flash of light filled the cosmos, and as the universe expanded, that light stretched with it to longer and longer wavelengths, through the visible range, to the infrared, until now. That flash of light remains as a faint glow of microwaves filling the entire sky. The glow that Robert Wilson and Arno Penzias detected with this antenna.
Penzias and Wilson's discovery of the microwave background is what made cosmology a science.
It suddenly made you realize that history was being made. Here you were, and suddenly the universe, as understood by man, was different to what it had been like yesterday.
All of a sudden you had data. And you really tested a theory. You had a theory that said the universe started with this hot Big Bang. And what Penzias and Wilson saw was this leftover heat from the Big Bang.
Their serendipitous discovery was so important, it won Penzias and Wilson the Nobel Prize.
The actual ceremony in Stockholm was kind of a blur. I never have quite gotten over the feeling of not being a grown-up, that other people are older, smarter, and so forth, and that I don't think that ever leaves.
When the Nobel Prize was announced, I think probably one of the first things I thought about was, do I really deserve this? And should my name be on the same list with Einstein, which just seemed completely wrong. Over the years, I guess, I've come to understand that the Nobel Prize is given for discovering something, not for being the smartest person around. So while there are much smarter people around, we did something significant, and I feel comfortable with it now.
Now that we know what to look for, it's not all that hard to detect the Big Bang. Take an ordinary TV set, the old-fashioned kind, before cable. All you need to do is change the channel until you come between two stations. Most of that static comes from stray local radio waves hitting these rabbit ear antennas. But, amazingly, about 1% of the snow and noise comes from microwaves produced in the Big Bang itself. Right now, we're all eavesdropping on the birth pangs of the cosmos. The discovery of the Big Bang was revolutionary. In February 2003, that revolution takes off. In just over a year, WMAP has sampled more than 2 million points in the sky. Finally, almost 4 decades after the faint glow of the Big Bang was first detected, the satellite delivers a beautifully detailed picture of the peaks and valleys that mark where the matter lies in our newborn universe. So David, this is it, huh?
This is the map. This is what the universe looked like 380,000 years after the Big
Were you the
Bang.
first one to see this when it came from the telescope?
I think I was the first one to see this particular version of the map.
What did it feel like?
Oh, it was so cool. I mean, you know, to know that you're one of the few people who get to see this first was just awesome.
In this version of the WMAP picture, the peaks are hotspots that show where the superclusters of galaxies will form. The valleys will become empty space. Most important, this pattern is so detailed that cosmologists can now piece together almost the entire story of what happened during the birth of the universe to create the structures we see today. The Big Bang itself remains shrouded in mystery, although WMAP tells us that the universe's birthday came 13.7 billion years ago. Using WMAP data, we can reach back almost to that beginning, at a time when the universe was tiny, much smaller than this pearl. We're not sure what came next, but our best current idea is that an event called inflation triggered a hyperfast expansion, enlarging the universe a trillion fold. But just as suddenly as it began, inflation stops, leaving behind a dense, hot, violent universe. All of space is filled with a zoo of exotic particles, the precursors of ordinary matter. And all the light within the cosmos is trapped in an endless pinball game, bouncing off these particles. But as the universe continues to expand, it cools. Until, at last, 380,000 years after the Big Bang, temperatures fall to the point at which familiar, stable atoms can form. In that instant, the primordial fog clears and the light from the Big Bang flashes free, forming the image that WMAP has captured, a true baby picture of the cosmos.
The really remarkable thing that MAP found was the universe was incredibly simple. I think we're now close to the right story for how the universe evolved from a second or so after the Big Bang till today.
But not so fast. There are no signs of life in this picture. The WMAP universe contains only the simplest atoms, mostly hydrogen, just a single proton with one electron, along with a little bit of helium. Living chemistry requires more complex building blocks: carbon, oxygen, iron, and the rest. But if they didn't exist in the early universe, where did they come from? Recent supercomputing simulations show the infant universe filled with vast, billowing clouds of hydrogen. Almost immediately, the clouds begin to condense, pulled together by their own gravity. As hydrogen piles on, the central region grows more and more dense, until something brand new lights up the universe: a star. These first stars are hydrogen giants, 100 times or more larger than our own sun. Such massive stars are short-lived, 2 or 3 million years at the most, and they go out with a bang. In explosions so big, they've been dubbed hypernovae. And it's with these cataclysms that the universe begins to accumulate the building blocks of life. All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They know that because they last so much longer than we do, we think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. The star begins its life made out of hydrogen and helium mostly, about 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spin.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel this stellar furnace, and so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing's blowing up. And you've made a supernova.
The supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium,
indium,
niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
ytterbium,
tellurium,
thorium,
iodine,
radon,
xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
indium,
actinium,
xenon,
thorium, protactinium,
cesium.
uranium. Done. That's enough elements.
We are all stardust. The carbon in our bodies, the iron in our blood, the calcium in our bones. Every last atom was formed in a star. Mix that light up into the visible spectrum, the rainbow of colors from violet to red. Zooming in on a galactic spectrum reveals a forest of bright and dark lines. Patterns that reveal the presence of particular elements.
Using spectra as our tool, we can tell you what elements exist in that galaxy: oxygen, carbon, iron, and we can tell you whether the galaxy is rich in those elements, has the broth cooked a lot, or is it still too dilute to make planets.
That's what Sandy will do tonight. Measure the amounts of heavy elements to determine each galaxy's readiness for life. Sandy and her team ultimately plan to examine 65,000 galaxies in all, in a massive census dubbed the Deep Survey.
There we go.
Oh, beautiful. Oh, isn't that great?
Here are the results, hot off the telescope.
This is fantastic.
That's the kind you're talking about.
That's oxygen, and oxygen here.
This bright spot marks the presence of oxygen in a galaxy 5 billion light years away.
Just purely by coincidence, we're looking at galaxies. Their light left just when our sun was forming in our own galaxy, right? And so this one here...
Sandy uses the sun's level of oxygen and other heavy elements as her benchmark. If a galaxy has a similar mix of elements, then potentially it could support the same living chemistry we find here at home.
So that galaxy would be a really good place to look for for planets because it's even more abundant in metals than our own galaxy is.
Into a projected 10-year observing program, the Deep Survey team has already detected thousands of distant galaxies that are rich in the elements of life. And that leads to a startling conclusion.
Our universe is hospitable to life. There are billions and billions of galaxies everywhere, cooking elements, making stars that are right for solar systems. The habitat for life is everywhere.
That's no proof that life itself exists anywhere else in the universe. But Sandy's work does confirm that the elements essential to life as we know it are widespread throughout the cosmos.